In the first lecture, entitled Chemical Composition of Compounds 1, we mentioned different types of compound formula. In this lecture, we're going to figure out how to generate empirical formula from mass data and how to compute the molar mass of chemical formula. Let's do some problems in which we use experimental data to calculate the empirical formula for compounds. We'll look at an example involving a compound we've seen in previous lectures, ammonia. In making 54.0 grams of ammonia, we find that it took 9.6 grams of hydrogen atoms and 44.4 grams of nitrogen atoms in a synthesis reaction. So what is the empirical formula for ammonia? The computation begins by first converting the given masses of the elements to moles of the elements using the relative mass ratios on the periodic table for the element. We then divide the moles of each element by the element that has the least number of moles, in this case nitrogen. In this step, we are in effect finding the integer mole ratio of all the elements in a compound relative to the atom that has the least number of atoms in the final empirical formula. We will round off to the nearest integer value if it's close to an integer already, trusting that Dalton's law of multiple proportions applies, which states that compounds are made up of simple whole number integer ratios of the elements. Now, we could have converted the moles to actual numbers of each atom, but that would be redundant. We are assuming that the moles are directly equivalent to the number of particles. Now it's a simple matter to write these ratios as a subscripts in the empirical formula. For ammonia, the empirical formula NH3 is also the molecular formula. The ordering of the N and H in the formula are not important right now. Those rules are coming later when we do nomenclature. Now at times, we may still need to multiply each ratio by a common integer so the ratios give us whole number ratios. Now we don't need to, but many folks like to see empirical formula without the decimals, and they want to see a result that doesn't have partial atoms in the empirical formulas. Let's see what I mean in the next example. For this example, we have a compound that was found to have 63.15 grams of carbon, 5.30 grams of hydrogen, and 31.55 grams of oxygen. So what is this compound's empirical formula? Well, we run the computations as we did in the previous slide, but that at the end of the computation, we come up with final ratios of 2.67 for carbon, 2.66 for hydrogen, and 1 for oxygen. The values for carbon and hydrogen are not even close to integers. Now we can stop here and just write the results, but it does look a bit funny. We want integer values if we can, so we multiply all the subscripts by the smallest common multiplier. That will give us whole numbers rather than decimal values. The smallest common multiplier in this example happens to be 3. As Dalton observed, most molecules are made up of atoms in small integer values, so the smallest common multiplier most of the time will lie between 1 and 5. The final empirical formula without decimal ratios is C8H8O3. Let's do another example, but this time we'll have just the mass percentages of each element in the compound. We find that for the compound hydrogen peroxide, that 5.9% by mass is hydrogen and 94.1% is oxygen. Obviously, the percentages should add up to about 100%. Now we begin by assuming we have 100 grams of hydrogen peroxide. If we multiply 100 grams by the percentages of each element in the compound, this gives us 5.9 grams of hydrogen and 94.1 grams of oxygen, analogous to the magnitude of the percentages. Now we run the computation as we did in the previous two slides. For this example, we obtain the interesting empirical formula HO. Notice this is different than the empirical molecular formula for water, right? H2O, which also has only the elements hydrogen and oxygen. It's important to realize that combinations of the same elements can give different elemental ratios and different compounds. This phenomenon is very common in organic compounds consisting of carbon and hydrogen elements. Furthermore, it turns out that in the case of hydrogen peroxide, that the empirical and molecular formula are not the same. We'll get at how to get the molecular formula from the empirical formula in the next lecture. Before we can move on to determine the molecular formula, we need to learn how to calculate the molar mass of any given chemical formula. What do we mean by the molar mass of a chemical formula? Well, the molar mass is the actual mass in grams if we had 1 mole of the compound with a given chemical formula. In the case of empirical formula, this is just a mathematical quantity, but for a molecular formula, this molar mass is the actual mass of 1 mole of the compound. Let's do an example. If we had the following chemical formula, CH4O, which happens to be the molecular formula for the substance methanol, we would first look up the relative molar masses for each of the elements in the molecular formula and assume they have the units of grams per mole of the atom. We assume we have 1 mole of the substance CH4O. From the subscripts, we know that if we have 1 mole of this stuff, that we must then have 1 mole of carbon, 4 moles of hydrogen, and 1 mole of oxygen atoms. Mathematically, what we're doing is multiplying 1 mole of the substance, in this case methanol, by the mole ratio of each of the different elemental atoms using the subscripts in the chemical formula. The computation gives us the moles of each element in the compound and is consistent with what we expected. We then multiply the moles of each element by the relative molar mass of the element found in the periodic table. Again, we're assuming the relative mass numbers are in the units of grams of the atom per mole of the atom. At this point, we have the mass of each element in 1 mole of the substance, methanol. Now we add up the masses of each element, giving us the molar mass. So in the case of 1 mole of methanol represented by the chemical formula CH4O, we arrive at the molar mass of 32.05 grams. Keep an eye on the significant figures, which will ultimately be dependent on the precision of the relative atomic masses from our periodic table. Periodic tables can vary as far as the number of significant figures they choose to report. So, in summary, to calculate the molar mass, we look up the relative atomic mass on the periodic table for each element in the chemical formula. We multiply each relative atomic mass by the subscript in the chemical formula and add all the masses together. We remain aware of the sig figs of the relative atomic masses, and assuming all subscripts are exact values, the result is the mass in grams for 1 mole of the substance represented by the chemical formula. Now next time, we'll look at using an experimental value we can obtain from a device called a mass spectrometer that will help us bridge the gap between the subtle difference between an empirical and a molecular formula. See you soon.